Welcome everybody on Zoom in the lecture hall to the course Information Systems for Engineers. So we'll be spending one semester together, and I will teach you the basics of relational databases, of the SQL language, of how to store and how to manage your data. Hopefully it will be useful for your projects later, you know, semester projects, master's thesis, PhD thesis, and so on. So this first lecture is a bit special because I'm not actually going to go into the material and to you know, teach you already the details of everything that we'll be doing. It's more of an appetizer lecture and a motivation lecture in order to explain to you why we have database management systems. Why don't we just use Python and data frames, right? Which is quite a hype nowadays. But there are reasons, and there's a whole theory behind it that is already 15 years old now, and that established itself. I like to think of data as something that is like matter. In the sense that when you do physics, you study the real world. You experiment, you play with atoms, with molecules, and so on and so on. And then you just, you know, build hypotheses and try to figure out if your hypothesis is correct or not, right? It's a notion of falsifiable theory. Well, in data science, it's pretty much the same. We also manipulate data instead of matter, but data, as you will see, has a lot in common with matter in the sense that it assembles together in order to form shapes that you can then manipulate as you query it, right? So to put things in perspective, data science in particular, there is a common way of looking at how humankind does science in general. In the very early days, so that was actually thousands of years ago, we didn't have computers, right? So mathematics and physics were invented. It slowly emerged from a lot of philosophers, but mathematics and physics was our scientific relationship with the world, right? So how are they different? So I like to think of it in terms of model logic, in the sense that mathematics is something you can do from your armchair, right? You can derive the numbers and the real numbers and so on. So it's a lot of theory. And of course, some philosophers might disagree, right? But you could almost argue that mathematics is necessary. It's the way it is, and it couldn't be otherwise, right? But physics, experimenting, you cannot do from your armchair. You have to go out and experiment and actually see how the world is. Why? Because the world could have been different. What if the speed of light had been different? What if the masses of the particles had been different, right? So you need to make experiments in order to figure out why the world is the way it is and not in another way than the way it is. This is called contingency. And it means that it's not necessary, and this is why we need to go out and see the world. Now, I know there's also theoretical physicists that do a lot of things from their armchair, and it's actually pretty cool. But at some point, you need to see if your theory is actually in sync with the world, okay? And recently, that's actually in the last century, we had computers. And computers allowed us to automate a lot of things. And this is how computer science was born. It's a bit like mathematics, but it's a mathematics of computation. How do we theorize the notion of computability, running programs on a computer, and so on? So you have a whole field of theoretical computer science as well, software engineering, and so on. So I put it in the same column as mathematics, but simply because that last missing part right there is actually data science. In a way, data science uses computers, so it's like computer science, but it's also like physics, because you might have heard of hypothesis testing, for example, in statistics. In data science too, you do hypotheses and then you test them on the data. So it's the same as physics, except that you have one more intermediate level with the world, is that you first collect the data and then you analyze the data. In fact, at CERN, that's exactly how it's done. So when you, for example, for finding the Higgs boson at CERN, so you might think, okay, you just turn on the LHC, right? You turn it on, you send over a few particles, and oh, here, look, here's a Higgs boson, right? This is not how it works. This is not how it works. You actually let the particles collide for a while, and then you collect the data, massive amounts of data, so much data that you can actually not even store all of it. So you have to actually quickly make decisions on what to store, and you still end up with petabytes of data. And later you query that data. And that's actually a database problem. You have to query the data coming from the accelerator in order to find the Higgs bosons or whichever particles you are looking for. Okay, so I hope that this makes sense. So this is for all sciences in general, this is kind of the 4 ways of doing science. And we had ancestors that were very wise already at the time, like Plato, that a good decision is based on knowledge and not on numbers. And this is why it's absolutely not a trivial field at all. Okay, what's coming next now is a history of databases. I would like to go back a long time ago, thousands of years ago, and roll the entire history. Of course, it's going to be a bit accelerated because just in a few minutes, but just to give you a sense of how things have actually evolved, and in particular, that databases are not as young as you would think. You might think, okay, that's a computer thing, so it's just, it's been a few decades old. No, 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 it's thousands of years old. And the reason is that if we go to the prehistory, I'd actually define what I mean with prehistory and history. Back then, we didn't have any computers. We didn't even have paper or anything to write on. So the only thing that we could do is use our brains. So our ancestors were using their brains, and they stored in their brains everything that was going on, all the major events and so on. And so the way that you would share this information is by speaking or by singing. You also had people who were singing the events. And of course, they were focusing on everything that had to do with the kings and the emperors and so on, right? So this is how it was at the time. But you had to continuously speak and sing to make sure that every generation would still have the information and the data and keep it. So as soon as you stop speaking or singing, the information is lost, right? And then came a major revolution. That's the revolution of writing, where that's 3,500 before the Common Era, the invention of these clay tablets. The way you would basically use these little sticks and then print and then heat it up in order to keep it frozen, right? So this is how clay tablets actually work. And you have clay tablets that are actually stories. So this is basically text, right? It's explaining things. It was a lot also for inventories, for accounting and keeping track of inventories, but it was also with the goal of history, remembering what was going on, right? They already had that in mind. But the next slide is actually probably even more exciting than this one, because this here is thousands of years old. This is a clay tablet. And I don't know, but it reminds me a lot of a spreadsheet software running on a tablet. A tablet, not a clay tablet, but these modern ones that we have now where you can actually slide and swipe, right? And that gives me the goosebumps because this is actually a relational table. This is a relational database. This is a relational database. What is stored in here is actually numbers that can be the sides of a right triangle, right? The Pythagoras theorem, like 3, 4, 5, and so on. And back then, they already knew some of these numbers. The use of that was for construction. You needed to build right angles. So if you knew which sides you can measure in order to get it. And another reason for that especially in ancient Egypt, whenever there is a flood, you need to keep track of who owns what land. This is also a motivation for having this knowledge about right angles, right? But this is probably the most important slide of today, actually, is that relational databases, which we will study in this semester, in this course, are thousands of years old, right? Then came another revolution, because as you can imagine, even though now we found a solution to the problem of preserving information over centuries and millennia, we still have a problem with copying the information. Every time you want to make a copy of a clay tablet, you just need to do it all from scratch. And this is why you had actually people working on full-time jobs in order to make copies of texts, right? In particular, monks in the Middle Age. This was actually solved. It was solved with the invention of the printing press, where people figured out a way, Gutenberg, they figured out a way to basically prepare these little square. Actually, Buchstaben in German actually comes from that, and then you assemble them to form text, and then you just put it against a piece of paper, and it's going to just with the ink print the text on the paper. And this is how you massively reproduce the same text. This is what gave rise to the golden age of newspapers in the 19th century everywhere, because we had a way to actually reproduce this massively. All right, maybe I can make that a bit lower. I realize it's hiding a bit. Okay. So then came computers. Computers automated things. You basically do the same thing, but faster. So the first computers did not use electronics or transistors. It was actually mechanical, right? The very early ones. An abacus could be considered an early computer. Also, the notion of digital is actually ancient. The yin and the yang were already the bits, the 0 and the 1. So computers allowed you to automate things, and with the transistors and then reducing the size, we could at the same time reduce the power consumption, increase the speed, and so on and so on, right? But computers, I'm not saying it was a non-event, right? Of course, it wasn't a non-event, but it was just about making things faster. That's pretty much what it is about, in automating things. Okay, so now we are getting closer to today. In the 60s, we had file systems. So the way that this worked is that you had your hard drive, and you could, you can create directories and files on your hard drive on a desktop or laptop. And people were working directly manipulating files on their hard drive, right? They wrote computer programs, and then they were reading the files and then doing something with it, maybe extracting information, doing things with that, and then writing back files to the file system. This was actually quite low level. This was quite low level because you had to deal, you could not manipulate the data if you didn't know how to program, how to read from a file system, and so on and so on and so on, right? But then the database history actually started in 1970. 1970, this is the pivotal year. Because in that year, somebody called Edgar Code had an idea. He realized that this whole way that people are handling their data, directly reading from disk and writing complicated programs and rewriting all over the same algorithms and so on, it's too complicated. It's too complicated. And then next to that, he had another realization. Is there an issue with the laptop? Oh, yeah, that happens. Yeah, also happens this week in big data. All right. So he had, next to the idea that it was too complex when people were directly reading and writing from the file system, Edgar Code knew that tables are very intuitive to mankind. First, because they are thousands of years old. As I just showed you, we have them on clay tablets. So tables, everything understand. But even because very recent studies trying to figure out what people understand best, when you publish information, for example, in newspapers or on websites, what is it that people understand best? Is it tables? But maybe it's pie charts, scattered plots, histograms. What is it that people get best? The one thing that came out of these studies is tables. Table is what people understand best. This is almost universal and thousands of years old. So Edgar Code thought, okay, since we know that tables are so intuitive, why don't we try to structure our database systems, the access to databases and how to manipulate data in such a way that we let people think in terms of tables, something super simple and just manipulating tables. All of the rest, writing to the disk, reading from the disk, these complex programs, that should be done just once by experts or specialists, who sell you some piece of software, but the users should just reason on tables, right? This is the major idea for relational database systems as they were invented 50 years ago. Then, of course, things continued to evolve, and there is a whole history of that, is that, for example, in the 1980s, we had C++ emerging, then in the 90s, Java, and so on. And then at some point, people started moving over to object-oriented programming, and then there was the problem of connecting that to databases, right? So this actually gave rise also the years 1990s to data cubes, which we will also study in that lecture, so business analytics and so on. All right, now I'm coming to the lecture scope. So, oh, now I understand. I was like, why was that slide missing? I just swapped probably the lecture scope slide with the rest. So 1970s, the relational tables, 1980s, the object-oriented programming, and in the 2000s, there was a whole new generation of databases You see the key value stores, the triple stores, the column stores, the document stores. These were actually recent technologies that actually were invented because we had so much data and it wasn't necessarily fitting in tables that we needed to come up with other technologies. This will not be part of that lecture. It's actually big data for engineers, right? The next one where we study all that. In this lecture, we'll focus on databases and specifically relational databases. So you probably heard of that pyramid, right? You have data, you turn it into information, into knowledge, into wisdom. We'll focus on databases. Right here, we are not going to do machine learning or artificial intelligence, even though relational databases enable you to then go into machine learning and artificial intelligence. Why? Why? Because the inputs to many machine learning algorithms are actually relational tables, where the features are in columns and the labels in columns as well. So this is why relational databases also are useful to understand for machine learning. All right. So this is the lectures that I have. So I have information systems for engineers, which we have this fall. So this is where we are right now. There is a continuation of that lecture, Big Data for Engineers, in the next spring, which explores the more recent development. However, you can take it in any order. So some of you might have taken Big Data for Engineers. Did anybody here actually already took Big Data for Engineers? Some of you, right? And that's totally fine. You can take it in any order, right? So now it's basically, you know, like in the movies, when you make a prequel of a movie, right? So this is basically the prequel of Big Data for Engineers. All right. And big data is another one actually that's only for master students in computer science and data science, but it's actually very similar. It's just that here I specifically tailor it to other departments. So I don't assume that you have all the prerequisites that would be taught at the bachelor's level in computer science, right? So this is why I actually made two different lectures. All right. So now I would like to know a little bit more about your background. So we are going to use the Clicker app. It's also right here at ETH. So why don't you take either your smartphone and then download from your store Edu App 3, or you can also take a browser and go to the website, this address right here, eduapp-app1ethg.ch. It doesn't matter if you're in the lecture hall, if you're online on Zoom with us, you can in any case participate to the poll. All right, so I give you few seconds to just make sure that you copy this address right here. Yep. Maybe we find a way in the long term to make it permanent. All right. So you have the address right here, or you download from your app store. Then I'm going to switch my screen. Right here, not this one, this one. Okay. So if you didn't have time to copy the address, you can still see the domain, right? eduapp-app1.ethg.ch. All right, so I'll give you a bit of time because it's the first time we use it, but I'll actually be using it a lot during the semester, right? It's also a way of having a bit of interaction and make sure that you can participate both in the lecture hall and on Zoom. Oh, we have a lot of mechanical engineers. So electrical engineers, mathematicians, biologists, physicists. Oh, we have more theoretical physicists. Okay. Robotics. All right, does anybody need more time in order to make this work since it's the first time, or please let us know. Okay, seems okay, so I'll just go ahead and continue. I'll keep it open so that you can still make it work. All right. So now, if I prepared everything correctly, normally, I should be able to land back exactly where we were. There. Okay, so now this is the awesome TA team with all the TAs who will be with you during the semester. You can already see Andrea, who is right next to me here, moderating the lecture. Thank you for that. So Andrea is making sure that to monitor the Zoom chat. So if you have questions, you can ask them on Zoom in the chat. Do not hesitate, and Andrea will make sure that I answer. In the lecture hall, you can also raise your hands at any time, and we have this this amazing catch box that you can speak in, and you can just throw it, you know, without any fear of breaking it. So you can ask questions and participate anytime during the lecture, right? Never hesitate to ask questions, because, you know, I know that many of you are shy or maybe do not dare asking questions. Well, first, you can also paste on Element if you prefer pasting in the chat rather than raising your hands. That's fine as well. What you should know is that it's safe to ask questions. There is no such thing as a stupid question, right? This is a university and we are learning. And very often, when somebody asks a question, half of the people in the room will feel like, oh, I'm so happy that she asked this question, because I also had that same question and I didn't dare to ask it, right? So never dare to ask questions to make sure that you understand, or you want to slow me down a little bit. I know that some people actually like to accelerate things when they look at the recordings. So somehow you can increase to 25% in order to make me speak faster like that. Anyway. So you see, you have a lot of possibilities. You can interact over Zoom in the lecture hall. You can watch the recordings and so on and so on. You have the chats during the week, Elements. All right. So who are the other TAs? Do you want to? Yeah.
One quick thing. If you were at Zoom, please ask question using Element. I have Wi-Fi is a little unstable this morning, so I don't want to miss your question. So if you're on Zoom, please use Element instead. Thank you.
Thank you. Yes, that's a good point that actually Multimedia Services told us, is that when everybody is in the lecture hall, it's important not to be connected to Zoom at the same time, because the Wi-Fi bandwidth of the building cannot sustain this. That's exactly the reason why we also have the Element chat open, so that you can connect to it as well, right? Okay, so here's the team. So we have Nobi, who is the co-head TA together with Manuel. We have Amir, we have Tolga, we have Marcin, and we have Mark, who are the TAs. So maybe a big applause to welcome them, and they will be interacting with you. All right. Now, here comes an overview of what we are going to do. We are going to start studying relational databases. I'm going to alternate between theory and practice, right? Because theory can be quite heavy to digest, and then in the week after that, we just do a bit of practice, then theory and so on. So next week, we'll look into the relational model. We will formalize with math what a relational table is. Do not worry, it's not going to be math formulas all over the place, because it will be visual also, right? The table is very visual, but still we'll have a bit of math, right? Then we will be using SQL to create and modify tables. And by that, I mean the attributes of the tables and the types of the tables, right? So this we'll do in 2 weeks from now. Then we'll look into the relational algebra. Yes, algebra, just like addition, multiplication, and so on. You can also have something equivalent working on tables. So this is actually beautiful. So selection, projection, aggregation, and so on. Then we'll be using SQL to query tables. So that's the application of the relational algebra. In the SQL language, you'll be able to manipulate tables right from the comfort of your Jupyter notebook, right? Directly interacting to a database called PostgreSQL, which you will be using. All right, so this will be the basics of relational database systems. After this, we will move on to an advanced part of the lecture where we take things to the next level. What we will do is spend probably 2 weeks on what is called, it's not super fancy, database design theory. Why do we have database design theory? It has to do with best practices. if you just go ahead and design tables and throw your data in there without too much thinking, you're going to run into problems. It's going to be slow, you're going to have inconsistencies in your data and so on and so on. This is why plenty of people came up with theory in order to support you and give you a set of best practices of what you should do and what you should not do in the way that you design your table. This is also going to be useful for you when you have to store your own data in a system. So we will look into what is called normal forms, we will look into functional dependencies, and so on, right? So this will be a lot of theory. In the week after that, we will look into indices. What are indices? It's something that accelerates the execution of queries in a database. That's something you don't have if you use directly a language like Python. If you use SQL or a database, the system is able to build indices on the data. Think of a book, you know, when you have a book and you go at the end of a book. At the end of a book, there is typically an alphabetical list of terms that you can look up together with a page where you can find them in the book. This is an index. In fact, in relational databases, we also build indices like that in the background. And then it's magic. With the same query, with or without an index, with an index, it will be massively faster. So this is what we are going to look at. And I'll also teach you how you can actually build indices with just one line of code in SQL. Then it will look into the architecture of the system, what there is inside a relational database system. How does it actually store things on disk? Because eventually it comes on disk, right? But it's just that it isolates you from that. So you don't have to deal with that. But we'll still look into how it looks like just out of curiosity. All right, and then at the end of the semester, we will look into data cubes that are a different shape of data, very popular in business analytics, right? It's typically when you have sales data and you want to slice and dice it by country, by products, by salesperson, and so on and so on. So this is what data cubes are. We'll look into how we can actually store them in a relational database, in tables, and then query them. And then at the end, I'll have an outlook towards big data to make a transition with big data for engineers. All right. Any questions so far on the content? Yes? Maybe the catch box? Here.
About some of the non-relational database, like eValue or something.
Let's set up the sounds. There's a bit of echo.
Hello?
Yeah, now.
So I see that we are mostly talking about relational database. Do you have any plans for just talking a little bit about some of the non-relational database like key value storage or something?
So yes, this is actually part of the course series, but not this one. So this is something we'll do in big data for engineers. In big data for engineers, we'll look into JSON databases, XML databases, document stores, column stores, and so on, white column stores. So this is part, basically, if you come back in spring, after you took this lecture and then take the other one, then you'll have the complete coverage of both relational and non-relational, right? But it's a good question to ask because indeed, in the past few years, there has been an evolution towards non-relational databases and they became quite popular. I have to tell you though, and this is actually why this lecture is just as important, is that even though we have non-relational databases, I would say that 80% of the data today would still be best handled by a relational database, right? Because a lot of data fits in tables and these systems are 50 years old. They are extremely robust, right? And basically, if then you learn about non-relational databases, what I'll teach you in particular is when and when not to be using other kinds of databases than relational databases, right? All right. You could almost, by the way, consider that this is a non-relational database, right? So the data cubes part, because data cubes are an alternate shape of data, right? And I'll say a few more words in just a few moments.
Thank you.
Right? All right. Just checking the time. Okay, so here's how it works. We'll have the weekly lecture, just like today, in Friday from 10 to 12. You can attend in the lecture hall right here, like all of you. You can attend on Zoom. I see we have 37 people on Zoom right now. So you see, you have the choice between the two. And since I have the green screen right here, I make sure the experience you have on Zoom is also good. This is also recorded. It will all be on YouTube. So that means in particular that you can also watch us from the future if you prefer. But you cannot ask questions because that we don't know how to make work. But you can do that. And also that's useful, again, to accelerate by 25% to make me speak faster and also to prepare yourself to the exam. You can go over something that you didn't quite understand again. Then we have the exercise sessions with the TAs. So we have 1 hour Fridays from 4 to 5. So that would be in the afternoon. And then also the same the next Monday, 3 to 4, but it's either or, right? You don't come to both, you pick depending on your group, either you come on Friday or you come on Monday. We added this for extra flexibility because maybe some of you cannot make it on Friday, so you have this extra option to come on Mondays. There will be no exercise session in the first week. Right, so there is nothing tonight. Do not come. There is nothing on Monday. We will probably put online, or the TAT will put online a first set of exercises, but it's not. It's special. It's basically a tutorial for Python. You know, just because we are going to use a little bit of Python on the high level to make things work. And the other one is how to install a relational database on your computer, even though I think now we are using Docker, right? I think Amir is preparing some Docker. So who knows Docker? Who doesn't know Docker? Okay, let me tell you what Docker is then. So you know how difficult it is to install things. Right, so we have different operating systems. There is Windows, there is Linux, there is Mac, and so on. So there are so many different operating systems that it's very hard to make things work across systems. So especially if something works on one of the systems but doesn't work on another, then it's hard to support, and it's also hard for you because then you can, spend time on search engine for hours trying to make it work. Docker is actually solving that problem. It can be downloaded on any operating system. And then you can just download directly some sort of black box that contains the installation of everything we need, like Postgres and Jupyter Notebooks and so on. So it's going to make things easier because then you can just go ahead and run it. And once it runs, it's going to be the same for everybody. So if there is an issue, it's likely to be the same issue for everybody. There was a little exception with the M1 chips of Apple last year, but I think that Docker fixed them, so we shouldn't have the problem anymore. All right, so this is what we are going to be using, and then you can actually query your data. But of course, if you want to try and install PostgreSQL just for fun, then you can do that as well. Okay, and then we'll have the written exam, which is 2.5 hours in the winter session. Do we have a question?
Yes. Will it be possible to prepone the exam for exchange students or take an oral exam earlier?
Mm-hmm. So here's how it works. It's a computer exam, meaning that it's going to be on Moodle. And in a computer room at ETH. There's some in Earlycon and some in the main building. For this reason, it is not possible to prepone the computer exam, like to do it in advance. And it is also not possible to take it at a distance because ETH doesn't have the technical support to organize that. However, for exchange students who are coming from other universities and right now here with us at ETH, and you need to come back for the next semester and you cannot be here during the exam session, then we can offer preponed oral examinations over Zoom. Right, so this is what we can offer. So if so, please contact us and we will see how we can organize that. A word of warning, however, for ETH exchange students, meaning that you're here at ETH and you go to an exchange next semester, this is not possible because ETH students have to take the exam like everybody else and it cannot be converted to an oral exam. It's just ETH regulations. If you have any worry or if you are not sure, please write an email to the examinations office and inquire about your situation, right? And they will help. All right, did I answer your question? On Zoom. All right, perfect. Any other questions? Yes, maybe the. Oh, on both the slides. Okay, maybe you can repeat the question.
Exercise sessions will be recorded. Is it low? Yeah, whether the exercise sessions will be recorded.
So right now, so let me see how we go about it. Right now, the exercise sessions are planned in presence in all of these rooms and with no components of online. It was our interpretation of the instructions of we have to go back to in presence. However, I tried to gather information on what we can do and what we cannot do. It seems to be that we would still be allowed to offer an online exercise session. That might still be a possibility. So if this is something, if you would have trouble attending in presence over this slot, please write to us. If there's enough of you, we can see if we can arrange something, that we create a new slot for an online session where you have a TA and everybody can join spontaneously also. And then we would, if the TA agrees, of course, we need to secure the authorization of the TA, but we can also record it if the TA agrees, right? So thank you for asking. You're probably not the only one wondering. So it's great that you asked, right? Who just to see, can you raise your hand if you would like an online possibility? So you see some of you. All right. So we'll take note of that and we'll discuss it in the TA team.
There's another question on Zoom. Is there a possibility to offer an exercise session at Hung?
At Hung? Oh, Hung. Oh, that's the first time ever that I have this question. Let's see, would anybody want to have an exercise session on Hung in the room? And on Zoom, please raise your hands.
Please raise your hands on Zoom.
If you want an exercise session on Hung there.
We have 5, 6 people.
5, 6, we'll discuss this. I cannot make promises, but we'll take it into account and we'll discuss this as well. For you too, okay, so 6, 7, all right. I think there was also a question in the back. Yes, maybe the catch box. Maybe it's a bit far away. I mean, we can throw it, but
long throw.
It's a very big lecture hall. Oh.
Okay, so I'm not familiar with the whole examination block that was mentioned in the performance assistance. So it said that it's like examination block for a bachelor degree program in computational science and engineering. So if I understand correctly, if I'm not in this program, then I can just take this course and not take other program like exams from the block, right? Or is it also applicable for everybody?
So this is about blocks. So at ETH, you have examinations and you have blocks of examinations. Because in some bachelor studies, the lecture can be part of a block of examination. If it's not part of a block, you don't have to worry about that. Which block is it part of?
It says examination block G2 in the, yeah.
In which program?
The bachelor degree program in computational science and engineering. But it's also said like version 2018. And there is something in the bottom saying that if it's not changed, it's applicable. But still, I don't know if it's applicable if I'm not in this program.
So I'll double check that because it used to be in a block exam of CSE. That's the reason. Are you in CSE?
No, I'm in robotics.
Oh, then I think you don't need to worry about that. For you, it's just going to be an examination. And if you get the credits, you can credit it according to the regulations of your program. Right? So I wouldn't worry. But I'd still check with CSE if they change anything in terms of block exams. If we can just remember, Andrea, make a note so that I look into it. Thank you very much. All right. So, all right. So the exam is 2.5 hours. It's normally done. We try to restrict ourselves to 60 questions. The goal is that you can leave earlier if you need to leave earlier, right? So it should be normally plenty of time. And that's going to be a computer exam. It's going to be similar to the quizzes we'll have during the semester. Yeah, I don't know if I told you about the bonus points. You can actually get an extra 0.25 points at the exam. If you solve, there's 3 weeks of graded quizzes in 3 weeks of the semester. If you pass 2 of these 3 weeks, you get an extra 0.25 points, except if you have a 6. But otherwise, you get an extra 0.25 points. So that's also a good opportunity to work during the semester and reduce a bit your stress during the exam. Okay, a few more paperwork things. please, everybody connect once to this website. It's a chat server called Elements. We used to use Mattermost in previous semesters, but we had to migrate. Please connect once here. You will not see much, actually. It's just in order to activate your account, because you need to connect with your ETH login and password, and then the system will have you. Then I will be able to invite you to the course chat room. All right, so this is why. So please do it just once, just so that the system will know that you are registered there. All right, so element.inf.ethz.ch. It's all hosted at ETH, right? It's not leaving ETH premises, so you're safe, right? It's all with us right here. Okay, it's the Department of Computer Science, to be exact. The second thing is that the course material will be available on this website, moodleapp2.let.ethz.ch. This is where we'll put the slides, we'll put the links to the recordings, we'll put the exercise material, and so on and so on, and any information also about the exam, the announcements. We'll either send emails over eDots or make them over Moodle. If my memory is correct, the TA team decided to use Element, right, for support.
Yes, so if you have questions during about the sessions or about the exercises, about the course in general, you feel free to ask on Element. That's our main channel for questions.
Thank you, Andreas. So exactly, connect right here if you have questions anytime during the week, and we'll try to answer. I think we usually say like within 48 hours or something, you know, that we try to give you an answer there. Okay. Okay, so far so good. Do we still have time until the break? Oh, I have 4 minutes. Can I say anything before? Maybe we should take the break, right? Then I take it from here after the break, and I'll talk to you about then a bit more about data information, what there is to expect and everything. So why don't we take a break? I'll see you at 11:15, right? For the continuation. It's time to get a walk, get a coffee, and so on, right? So see you around 11:15.